Hello, everybody. Welcome back to yet another session on IGCSE Physics. And today we're going to be doing past paper questions based on voltage divider circuits. In case you missed it, last episode we covered voltage divider circuits. But anyways, without further ado, let's keep cracking. Hey, Kaleem.
Thank you very much, Pugz. As always, welcome again, ZNotes fans. Let's get into this and do some past examination questions. As Pugz has mentioned on, they're not just voltage divider circuits. Very often students kind of get this confusion. What the hell is a voltage divider? Well, basically, as the name suggests, it's a circuit that divides voltage. Now, what kind of circuit would that be? Well, in its simplest terms, series circuits are voltage dividers. How? Well, when you have two components in series, what happens to the voltage? It adds up to the total. What you're going to learn today, and what you learned last lesson, is these circuits can be really, really useful, especially when you want something to be automated. Now, the examples I gave last lesson, nowadays cars, okay, that's the ones that kind of stick out in my head. A car, when it rains, the window wipers come on if it's set to automatic. The headlights come on if it's set to automatic. You might have lights, in your back garden that come on when it's daytime. Sorry, nighttime, not daytime. So it's like solar powered lighting. They'll collect energy all day, but then at nighttime, it knows it's nighttime. How does it know it's nighttime? There'll be an LDR in there somewhere, a light dependent resistor. So it's not like it's thinking. There are components that behave in certain ways under certain conditions that allow certain things to happen. Now, there was a lot of certain in there. What the hell does that mean? Guys, if you have a jigsaw and you know how it works, and then you've got this individual component and you know how it works, if you can put it in the right place, you can create a fire alarm. Put it in the wrong place, instead of a fire alarm, you've got an alarm when it's cold. You put an LDR in the right place, you might get a light that lights up at nighttime. Put it in the wrong place, and it lights up during the daytime. Now, in the first example, having a fire alarm or an alarm when something is cold, you could possibly think of examples where that might be useful. I'm struggling to think of a time where it would be useful to stick a light bulb on during the day, but I'm sure there's something. All right. So let us get into this. So, guys, here, a nice way to start this is to show you, like this on its own is a mixture of a series and parallel circuit. All right. It's useful to build up to where we want to go. It's useful to revise. This on its own, for a teacher would not be regarded as a voltage divider circuit, even though it does split the voltage, but it doesn't do it for an automated purpose, which you're going to see as we get towards the end of the lesson. So we've got a mixture of a series and parallel circuit. It's a nice warm-up. It's just to get us into the, the habit of, well, what's happening to current, what's happening to voltage, what's going on here. Sorry, that's not quite connected. It's kind of knocked itself off, but I hope you understand that connects all the way around. So it's asking, what is the relationship between I1, I2, and I3? Well, I1 is right there. I2 and I3 are here. So what's going to happen is I1 is going to equal I2 plus I3, because at this point it becomes parallel. The current splits up. So I1 equals I2 plus I3. Then it asks, what can you tell me about the relationship between I1 and I4? That's away over there. Well, they're going to be the same. Why? Because here the current splits, but then at the point Y it joins together again and it goes all the way around. So I1 and I4 are going to be the same. So the ammeter reads 0.80. Assume it has zero resistance. Now look, guys, they say this at IGCSE and it actually throws students off. What do you mean assume? Just always assume it has zero resistance at IGCSE, because at A level we teach you that that's not quite correct, but this isn't A level, it's IG or GCSE, and we're trying to make it simple. Then they say calculate the potential difference between X, which, let me just highlight this, is right there, and Y. And this is now all of a sudden students are like, oh, what's going on here? I don't know. There's 3 resistors. There's an I2 and an I3 and a 2 and a 3 and an R and an I4 and an I1 and a 6. I don't know what the hell's going on. Look, why am I warming up with this circuit? Because if you don't understand, I've stressed this over the last couple of weeks. Fundamentally, if you do not understand current, voltage, and resistance, I believe electricity becomes harder. Yes, you can learn to get by, but if you're going to take this on an A level, learning to get by is not going to last long. At some point, it's going to smack you in the face, metaphorically, of course. All right. So, how do you answer between X and Y? Because you're like, well, current goes that way and current goes that way. I don't know what's going on. Well, guys, they did you a favor by telling you, oops, the current here is 0.80. So we've got current here. You've got resistance there. And you might go, but that's not enough. It is enough. Because what you're supposed to understand is, yes, the current in each of these branches will be different. But they have one thing in common. The voltage is common. And I can hear some students go, yeah, I know what it is. It's 6. No, it cannot be 6. If that wasn't there, okay, I just messed that diagram up. If that wasn't there, then it's 6 and 6. But sir, they're in parallel, they get the same voltage. I know, they do get the same voltage, but it can't be 6. Okay, because this isn't a parallel circuit. It's not a series circuit. It's a mixture of both of them, people. So, just to say that it's 6, well, it doesn't work, because if, let's say that is 6 and 6, what are you telling me? This one gets nothing? That makes no sense. All right. I tried to kind of point this out to you the other day. I don't think a lot of teachers will point it out this way at IG. If they do, my apologies. But look, guys, this is how you do this. Treat it as a closed loop. What do I mean by a closed loop? I can go from one end. It's as if you're doing dot to dot. One of those maze things as a kid that you used to do, those maze puzzles, and you had to get from one end to the other without hitting a dead end? Well, that's what you're doing. See these two? Let's call it, I better not call it X and Y. We've got X and Y. Let's call it A and B. If you add A and B, it's 6. If you were to, let me use a different color, another closed loop. This is almost bordering an A level. I can hear some of the teachers cringing, but I think it helps students understand. If you add C and B, it adds up to 6. The point is, in parallel, they're the same, but you either add A and B or C and B. You don't do A plus B plus C. Okay, that's not how it works with the voltage. Why? Well, basically because here the charge is split up. Some of them carry the energy that way, some of them carry the energy that way. And then when they meet here, they all have to pass through B and give that energy. Okay, let's crack on. So, how do we find the voltage? Well, we've been given the current and we've been given a resistance. So all you need to do is 0.8 times 3, and it will give me 2.4 volts. So what am I saying? I am saying to you, yes, this is 2.4 volts. And yes, because that's 2.4 volts, that's 2.4 volts. And yes, this is 6 minus, 2.4 volts, which is 3.6 volts. I've probably jumped the gun here, but I want to give you an idea of what's going on. And let's just tidy up the untidiness and get rid of whatever that squiggle is. So 6 minus 2.4 equals 3.6. So now look, guys, 2.4, 3.6 gives me 6. 2.4, 3.6 gives me 6. The current, it's 0.80 here. Okay? We don't know what it is here, but we could find it very easily now because we've got a voltage and we've got a resistance. In fact, I'm jumping ahead. I'm pretty confident they'll ask this question. So we've got voltage. Yeah, okay. Now they're asking, what's the current in I3? So what's the current down here? Well, now it's hopefully much easier for you to answer. Because I equals V over R, which is, what do we call it? 2.4 over 2. And let me just have a little 2.4 divided by 2, 1.2 amps. So guys, if that's 0.8 and the bottom one's 1.2, what do you think the total current is? What do you think I1 is? I1 should be 2. What do you think I4 is? Well, if I1 is 2, I4 is 2. This is what I mean by understanding these black dots, these charges, they get to the junction, they split, and then they come back around, they join together again. Okay? Let's move on. So I3 was 1.2 amps, and then they said we want the resistor of R. So now they want, this might get a bit messy here. Let's just pick a different color. Now they want that resistor right there. Well, how do you do it? Well, I know that voltage is 3.6. And since I know I2 is 0.8, and I know that I3 is 1.2, now I've got a total voltage and I've got a total current. So what do? R equals V over I. Don't worry, we'll do this in the next page anyway. 3.6 over 2, and that will give me 1.8 ohms. So what am I doing here? You know, I know the whole topic's about voltage dividers. Well, technically it's dividing voltage. R is get 3.6. The other two I've got 2.4. That's a division of voltage. Is it being used in the sense as in the traditional sense of a voltage divider? No, we're building up to that. But we're talking about current, we're talking about voltage, we're talking about resistance. We are warming you up by using a simple circuit. Well, I say simple in regards to voltage dividers, a simpler circuit to start with. Right, let me find my cursor and just erase all ink. So guys, all you're going to see here is the exact same values I gave you in the previous page, and we get 1.8. So we found the total current, 2. We found the total voltage, 3.6. We found the resistance, R equals V over I, 1.8 ohms. So I've already shown you that. Okay, another very quick, nice warm-up, but then it does warm up quite quickly. State the electrical quantity that has the same value for each of 2 resistors connected to a battery when they are in series. Guys, the thing that's the same is, I want to hear you, current. Okay, current is the same. What's the same when they're in parallel? Voltage is the same, potential difference. Okay, next, here is our first potential divider circuit. Now, what's going on here? I want you to ignore that voltmeter for a second. What kind of circuit do we have? We have a series circuit. Now, you might be thinking, well, what does this do in an automated fashion? Right now, nothing, because right now it's connected to a voltmeter. Again, we are building up deliberately in level of difficulty. So what do we know about a series circuit? We've already said it, current's the same. What do we know about voltage in series? It adds up to the total. So these 2 components, the thermistor, that bad boy there, and the fixed resistor must add up to 9 volts at any one time. In fact, if they both had identical resistance, it would be 4.5 volts, 4.5 volts. But here is where the resistance is very, very unlikely to be identical. Now, what's the voltmeter for? The voltmeter is just going to try to build up this idea that the voltage is going to depend on what the thermistor does. Well, how does that help me? Well, instead of a voltmeter, imagine that was a bulb. Imagine it was a fan. Imagine it was another device. So depending, let's say the voltage was high. Well, if it was a light bulb, it'd light up. Let's say the voltage was high. Let's say it was a fan. It would, give you wind. It would blow air. Not blow air. It would move the air round and round. The point is, instead of a voltmeter, it could be a component which we're building up to. All right, so it's building up in difficulty. So let's actually answer what the exam question is asking. Let me erase all ink. Calculate the voltmeter reading when the resistance of the thermistor is 3.6 kiloohms. Now, guys, I want to show you 2 ways of doing this. When you only know about circuits and stuff in a basic sense, you're going to use method number 1. And when you get more advanced, you're going to use method number 2. And I'm going to do them both and I'll even change the color. Let's call this method number 1. The traditional way of doing it. I equals V over R. What am I going to do? 9 volts over 1,200 plus 3,600. Wait, oops, let me turn that off. That shouldn't have been there. My bad. Now, where did that come from? Where did the 3,600 come from? Where did the 1,200 come from? 1.2 kiloohm, 3.6 kiloohm. What am I going to do here? I am going to find the total current. So let's just do that. And let me put brackets in the right place for the purists. So 1,200 plus 3,600, 9 over that. And I get 1.875 milliamps, or 1.875 times 10 to the minus 3. Now what do I do? Because I know current is the same at all points in the series circuit, V equals IR again, and this is where students are like, you're using the same formula. I know, but now I'm only going to specifically look at that point. So remember, in a series circuit, current's the same at all points. But now I'm going to multiply by 3,600. And what do I get? 6.75 volts. If this is 6.75 volts, what do you think the 1.2 kiloohm resistor is going to be? I hope you're guessing it back home. 9 minus 6.75. Now, I said that's the more traditional way. You figure out the current in the entire circuit, then you do V equals IR. What do I mean by traditional? I mean early on in electricity, that's how you get taught. Find the current, know that the current's the same at all points, then do V equals IR. What's the other way? I've got a much quicker way, and I'm going to call this the voltage divider method. It's not the voltage divider method. Okay, it's basically simple arithmetic. All right. But I like to give it a name because kids want to give it a name. So what do I do here? Basically, the voltage in the thermistor is equal to the resistance of the thermistor. All right. Maybe I shouldn't have done it that way because I now want to say the total resistance, but I'll just write it. I was going to give that a T times. I really shouldn't have used T because now I wanted to say total voltage, but I'll just write the word. Not well thought out, teacher. All right. So voltage of the thermistor, big T, equals the resistance of the thermistor divided by the total resistance times total voltage. Now, guys, I can prove to you that this is all derived from V equals IR and the formulas for resistance in series and resistance in parallel. All right. But we don't need to go there. But if we do this, 3.6 or 3, let's keep it consistent. 3,600 divided by 4,800 times 9. And I'm not even going to look at it because I guarantee if you stick that in the calculator, it'll be 6.75 volts. Why do I like that better? It's one calculation, you get there quicker. That comes with practice. Is there anything wrong with doing the first one? No. You're figuring out current and then you're figuring out voltage. Whereas this formula on the right, this expression, it's taken into current already. I know you don't see it. We don't need to go into it. It's substitution of equations, but it works and it's quicker. Okay. So look, guys, I've shown you worked out, but now let's actually go through this and you'll find the answers are the same. So R1 equals R1, sorry, R equals R1 plus R2. This is method number 1, 4.8. I equals V over R, 9 divided by 4.8, you get 1.875. Therefore, V equals IR, you get 6.75. So that's the method I just showed you. Or the one that I prefer is R1 over the total resistance. In other words, what I did was 3.6 divided by 4.8. Now, you might be thinking, but sorry, you did 4,800. This is math. Because the 3.6 is kiloohms and the 1.2 is kiloohms, you can ignore the 1,000, all right? Because all you're doing is taking out the factor of 1,000. So you could write 3,600 over 4,800, or you can just do 3.6 over 4.8 times 9. I promise you guys, the answer will be the same. It'll be 6.75. Okay? No units, drop a mark. Okay. Now, let's take it up a notch. Here we've got the thermistor, but at the top we've got a relay coil. What the hell is a relay coil? When we do electromagnetism, you're going to learn this very shortly. It's a solenoid. It's a coil of wire wrapped round and round and round and round and round. When you put current through it, it becomes magnetized. Becomes a magnet. What do you think it does to this circuit that it's not actually touching? It's not physically touching it. It will cause that switch to slam shut, just like I showed you the other day. Well, what does that do? Guys, relays are brilliant little devices that allow small circuits to turn on larger, powerful circuits. You might be going, what do you mean by that? Well, look, some circuits have a lot of current going through them. Okay, they draw a lot of current. So it'd be very, very clever if you could press a switch and know that you're never actually directly touching the thing in behind. Let me give you an example, and it's an example that might not be scientifically true, but students can relate. If you've ever watched very, very old films, black and white, where they used to start a car, and what they had is they had this handle, they'd go to the engine and they would rotate it round and round and round and round to get this car started. Well, guys, I don't know if you're young enough to remember a key going into the car. You don't even use a key anymore. Push a button. In fact, you don't even need to be in the car to ignite the, start the ignition of the car anymore. You can flick a couple of buttons and away it goes. The point is, they are very, very likely using relays where you touch the small thing and it's touching on the big beast. It's turning on the bigger circuit. Why is that pretty cool? Because it means you are never in contact with the more powerful circuit ever. You're only ever in contact with the small circuit, the relay. That will never touch that. It'll turn it on, but it'll never touch it. So basically, the switch gets pulled towards the relay, and when you turn it off, this switch will be spring-loaded. It'll just move back. So anyway, the key part here is, how does this circuit work? Well, to understand how this circuit works, you've got to understand a jigsaw. Let's just pretend these are two resistors. What do we know about this? This part right here, it's a series circuit. What do we know? Current's always the same. Whatever it is, whether it goes high or low, it's always the same every point. What do we know about the voltage? They both must add up to 9. Now it's a jigsaw. I've now got a thermistor in there. How does the thermistor work on its own? Forget the circuit. How does the thermistor work on its own? Guys, when it heats up, resistance goes down, current goes up. But when resistance goes down, voltage goes down. When it's cold, resistance goes up, voltage goes up. And this is how I would explain it to students. Remember I said to you guys the other day, I explained it in terms of current and voltage, but today I'm going to not confuse you. I'm going to stick to voltage. Pick one. Pick one and stick to it. And I think voltage is the easier way of doing it. So, if I just focus on the thermistor, when it's cold, resistance high, voltage high. When it's warm, resistance low, voltage low. Now I'm going to stick that thermistor into the circuit. How does it now impact the circuit? Well, when it's cold, I just said to you, resistance high, voltage high. Well, if the voltage is high here, okay, let's just call it high V. Well, that must mean that's low. Do you think that thing is going to become magnetized? Nobody's asking you for numbers. The answer is no. It's not going to become magnetized. That switch is not going to shut. All right? Now, let's try it again. What happens? It's outside somewhere and it naturally gets warmer. So when it gets warmer, what's going to happen? Remember, we're focusing the thermistor on its own right now. Low resistance, low voltage. That's just a thermistor. Well, if that's got low voltage, high voltage. Well, if that's got high voltage, it's now become magnetized. The switch is going to shut and the buzzer sounds. What do you have here? You have a fire alarm. You have an alarm that goes off when it's too hot. We're not focusing on the numbers. We're only talking high and low. And that's what they do in the exam. They talk about high and low. They keep it simple. So how does this circuit work? And now I've explained both ways, guys. For the exam, you just focus on how it works. When the temperature rises, the resistance falls. Okay? The voltage across the thermistor falls. The voltage across the relay rises. So thermistor falls, relay rises. Remember why? It's a series circuit, this part. Its voltage must add up to the total. If one falls, the other one must naturally rise. Has to, because energy cannot be created or destroyed. It changes from one form into another. All right? The magnetic field of the relay closes the switch and the bell rings. So you keep it simple. Thermistor gets hot, resistance down, voltage down. Voltage of relay rises, becomes magnetized, closes the switch, buzzer sounds. That is a typical automated voltage divider circuit. So let's do another one. Determine which one of the following resistors connected in parallel with a 24 ohm resistor would give a total resistance of 8 ohms. See, these kind of questions, students don't like them because they're doing the whole thing in reverse. What they're doing is they're giving you the answer and they're wanting you to work it back. It's quite naughty, actually. So 1 over R equals 1 over R1 plus 1 over R2. Remember, that was one of the formulas. Or R equals R1 R2 over R1 plus R2. You can use any one of them. So here, I've chosen to go with 1 over 8. That's the answer. Equals 1 over 24 plus 1 over X. The resistor we don't know. If you rearrange, you're going to get 0.125, stick in your calculator, equals 0.042 plus 1 over X. What happens? 0.083, because what you're going to do is you're going to take 0.042 away from both sides, equals 1 over X. Rearrange, and you get 12 ohms. So normally what happens is you've got 24 and you've got 12 and they ask you to find the total resistance. But here they're flipping it on its head. So in the displays below, so this is another circuit problem, draw the parallel combination of resistors from A connected with a 6-volt battery. The circuit should also include an ammeter to measure the current in the 24 ohm resistor. Guys, this is where I feel a lot of students lose marks. They don't really know how to draw circuits. They don't really understand what the question's asking. It's basically asking you to do what you did in the last part, but in parallel. And then they also ask you to find the current in the 24 ohm resistor. So here is an accurate representation of what that circuit would look like, and you'd be asked to draw it. Do you need to draw the junctions? Not really, but it should be drawn. Okay, that little dot means junction. What does that mean? At this point, the current splits up, and at that point, the current joins together. Now, why am I doing it like this? Remember, all circuits are based on conventional current, positive to negative, but I really couldn't care if you did it in the opposite way, because it doesn't matter. So another student might think, oh, it splits here and comes together here. Potato, potato. It's no big deal. Okay. And then it says, calculate the current in each of the resistors when connected as shown in B part 1, sorry. So here's the key. How do you do that? It's a parallel circuit. Pugs, what do you think the voltage is in each of these resistors this time? And the reason I gave you this, because this is very similar to the first question I gave you with a slight twist.
You mentioned twist.
No, I'm not trying to be twisted here, Pugs, but this is very, very to the first circuit, except it's missing something to the very, very first circuit we did.
I'm going to try my luck and okay, so there's one thing that's different is obviously there's 24 ohms and 12. Okay, but I still want to go ahead and guess 6 volts.
Is 6 volts, okay, guys? And why wasn't it 6 volts in the very, very first circuit? Because in the very first circuit we had, that is horribly drawn.
Yes.
Horribly drawn. Let me go back and do it again. Because in the very first circuit we had an extra resistor. And that's the difference, people. In the first circuit, oops, sorry. change the color. We had an extra resistor. Now, guys, I know that's become a fuse for the purists because there's a line through it, but in the first circuit, there was a resistor. Here, there isn't one, so they both have 6 volts each. And what I hope you all realize now is, well, finding the current's easy because now I do I equals V over R, 6 over 24, I equals V over R, 6 over 12. And what I hope that will teach you is lower resistance, bigger current. Oops. Higher resistance, lower current. That's exactly what's happened there. Okay, but here's another voltage divider little circuit. And this is what we're trying to build up on. This time, yes, we've got a relay. Yes, that dotted line here exists in a lot of exam questions, but not in all. That dotted line merely represents the relay, that the coil and the switch are related. They're not connected, they're related. You know, they affect one another. Here we've still got a buzzer, but this time instead of a thermistor, we have a light-dependent resistor. Shock horror, it's a resistor that depends on light. Now let's focus on it on its own. What happens with an LDR? Light shines on it, resistance goes down. No light shines on it, resistance goes up. You need to know that part. Now let's stick it into our jigsaw. I call it a jigsaw, but I hope you understand what I mean. Now we've got these two in series. What do we know about a series circuit? Current's always the same. Voltage adds up to the total. So let's say this was 6 volts. At any one time, this plus this must equal 6. So what happens? I'm just making it up. When light shines on this, I already told you, resistance goes down. Well, if resistance goes down, voltage goes down. If voltage goes down here, voltage goes up here. What will happen? That will become magnetized. That will slam shut. And the bell will ring when light shines on this. When it's dark, resistance here is high. Voltage here is high. Voltage here is low. So it will not shut that switch. So let's just go through the questions. What's the name of component Z? I've already told you, light-dependent resistor or LDR. Explain why B rings in bright light. In bright light, the resistance of the LDR is low. The voltage across the LDR is low. The voltage across the relay is high. Okay, remember, if one goes down, the other one has to go up. This magnetizes and attracts the switch, okay, the magnetic switch. Switch closes and completes the second circuit. And what I want you to understand is why a relay is good, because a small circuit can basically turn on a more powerful circuit. And last but not least, a change is made to one of the circuits so that B starts to ring when the temperature in the room rises. Well, before it was an LDR, light-dependent resistor. Well, if it's going to be dependent on temperature, what do we need? I hope you guessed it, thermistor. Okay, so because a thermistor depends on heat and an LDR depends on light. If I'm not mistaken, Pugs, I think that is us wrapped up for today. Guys, I hope you found that very, very useful, and I hope that will help you in your upcoming exams, which is 4 days away for paper 4. Okay, I know that the AQA have still got a little bit of time to go, but Cambridge, you're up very soon, 21st, I think, 21st, 21st. Thank you.
Yeah. Thank you, Kaleem. I hope this is useful. And as always, all the resources in the description below. Just a word, all the best for your exams.
Absolutely.
There's nothing to get really freaky about. Keep a cool head. Don't cram. Don't cram the night before. Never helps.
I actually would
Just
love.
keep a cool head.
I would
and hit
actually
the
love
button.
to add to
And
that,
Kaleem,
guys. Now listen, I know Pugs says don't cram the night before. You know, if that's your strategy, that's your strategy. But I would agree with Pugs. It's been proven that it's not an effective strategy. In fact, this might go down like a lead balloon. But the day of before my exam, the evening before, I was out with my friends playing football. I stopped about midday the day before my exam because you need to try to keep as relaxed as you possibly can. Listen, that is easier said than done. Nervous tension is always going to be there. Everybody has nervous tension, but the idea is to keep as calm as you can. So cramming the night before, you're tired. Pumping yourself with caffeine and Red Bull, I mean, you are like this, like shaking. Now, I know many people for years have got themselves to it, but you're not working to your optimal efficiency. Listen, I don't want to lecture, but if you were to think about your conscious mind, you're listening to me consciously and subconsciously, actually. But all your info is stored back here, right? And if I can just give you a little way of thinking about this, pretend there's a little pipe between here and here. When you're stressed, when you're tired, when you're trying to cram so much, see that pipe? It shuts. You ever been fed up and you're like, enough? Even though you kind of look at it the next day and goes, you know what, I totally overreacted. It's because you've had enough. How many tests, and everybody can relate to this, or exams have you walked out of and you went, damn, I knew the answer to that. You know why? Because the pressure's off, the stress is off, and that little pipe, if you want to think, it's not a real pipe, but if you want to think of it as an analogy, it opens up. All that info that you got back here comes flooding forward that you were not able to access while you were tired. So guys, look, it's not the best way to go about it. I know people do it, but it's not optimal. You got to try to get to sleep. Try, get any good habits. Why did I play football the night before? Because yes, I was stressed. But you know what? When you play football, you're exercising with your friends. This is a long time ago, right? When I was 16, 17, that was good 24 years ago, 23. It de-stressed you. I was able to sleep better. Was I still nervous to walk in an exam? Yes. Here's another bit of advice I'd love to give you. See, when you walk into that exam, don't talk to your friends. See, when you walk out of it, definitely don't talk to your friends. Go home, next one. All right? Because all that happens is, what did you get? What did you get? Oh, and then you just start to think about what's happened. It's over. It's over. You move on to the next. And let me tell you why. Because if you're carrying that stress and you've got chemistry or something the day after, then that exam suffers. I was always last into my exams, not late, last in. And when I left, I just walked straight out, straight home, away from everybody. In fact, I used to imagine this gold force field, but that's another lesson. Thank you very much. I hope that wasn't too late.
Yeah. Well, yeah, and all the best. Most importantly, have fun prepping up. It's kind of weird to say that, but yeah, enjoy what you're learning. We're gonna wrap it up for today. Next session's on Tuesday, and again Thursday is our past paper session. We're gonna be doing transformers, the electromagnetic force, and a lot of stuff, and motors. So do check it out, and yeah. Thank you guys. See you guys. Bye bye.